Good afternoon, ladies and gentlemen. Let me start with our afternoon session. Let me welcome you. This is our last session at this conference because tomorrow we have only two plenary talks. So, first of all, let me invite or welcome Kasia. The first talk will be given by Katarzyna Mish. This is joint work with Katarzyna Kaczmarek-Mayer and Michal Baczynski, and title is On Some Properties on Fuzzy Linguistic Summaries. Please take the floor.
Has to be consistent when it satisfies two properties, the property of non-contradiction and a property of double negation, and I will focus on them actually later. And this is our goal of this presentation, to investigate these properties, and you will see in which way we will consider them. So first of all, maybe I will recall the well-known definition of linguistic summary that was introduced in the 80s by Jager. And it is said that we have a linguistic summary if we have a set of objects, let's call it Y, and we have a set of attributes, A, that characterize these objects. So, for instance, Y can be a set of employees, and A can be a set of attributes like salary, age, and so on. And if we have these, also we need a summarizer. So, a linguistic value that will describe our attribute. We have a linguistic quantifier, for example, most, some. We have a truth of the summary, so the number from the interval 0, 1, which tells us how we can evaluate this summary. And optionally, we can have a qualifier, so additional how to say that property that will characterize some attributes. So, for instance, we have a summary like this: most of employees earn low salary. So we can write it in this way. So most is a linguistic quantifier, or we have most of young employees earn low salary. So in this case, we have a qualifier R, which is young. So as you can see, we have here linguistic quantifiers. So linguistic quantifiers can be divided actually in two groups. We have absolute quantifiers and proportional related quantifiers. So absolute is like about 10, not more than 10, and proportional are all about half, and so on. And we consider linguistic quantifiers as fuzzy sets. So as a fuzzy sets as functions, we can have increasing linguistic quantifiers, decreasing, or unimodal. So this is a kind of quantifiers that are increasing to the value 1, and then they might decrease. However, we can see following examples. So this is a little bit more complex example, because as you can see here, we have almost all young and with small experienced employees earn low salary. So this is again a linguistic summary. However, here we have this connective and. So we have two qualifiers, young and with small experience. That's why, in general, we can consider the following form of linguistic quantifier. linguistic summary, like here, where we have more than one qualifiers and more than one summarizers. And usually we will consider that we can have here just connectives and or, right? So this is the general form. And for this general form, we suggest a more general notion for fuzzy summary, fuzzy and linguistic summary. So having again a set of attributes, we consider that each attribute is a function that goes from the set of object to some non-empty set of real numbers. So we can have that X can be a set of salaries, for instance. Also, we need a set L of X, L of Y AI, which is a set of linguistic terms. For instance, it can be for the attribute age, we can have young, medium, old, depending on how we will describe this attribute. And here we define a family V. A family V as a family of all functions V, I, K, that their domain is the image of an attribute of a function AI, and it goes to the unit interval. So this is the set of actually family sets, this family. And this family we will consider as a family where we can find any summarizer and any qualifier. So we propose the following definition, that we have a principle like here that consists of a set of objects that consists of a set of attributes. We have some families, or we can say subfamilies, P and R. So the family P will be a family of summarizer, and R can be will be a family of qualifiers. And they are disjoint in this sense that if we have any element of the family B which is a summarizer, then any other fuzzy set that describe the same attribute can be a qualifier, and vice versa. So this is like here. And also we have, of course, a linguistic quantifier. So depending if it will be relative or absolute, we have these two domains for Q. And also for a fuzzy summary, we need a kind of a criterion to evaluate this summary, and to use that we define a family T. So this will be a family of functions that for any fuzzy summary will give us some real number from the unit interval 0, 1. And actually, it could be, of course, as we have here, this is a family of some criteria, but basically, it's a family of functions that can tell us about the true value of our summary. So in the most basic case, if we have just one element there, we will consider that there is a true function. And again, following the idea that were already in the literature, the idea of that, we extended the form of typical truth function. Because here again we have the family P and R, so we can elements of this family we can put in a sequence. That's why I numbered them in this way. And we have a values of each attribute for any object y I. And for this, also in a case that if we have more than one summarizer or more than one qualifier, we need to aggregate them And to do that, we use these functions, which can be conjunctions or disjunctions, depending if they represent and or. So having this, we suggest the following definition of the true function, which is most like the idea of Zadek, but we have more, it's a little bit extended. So here we have something like that, and here we have t with no index, and this is just a t-node. So we connect summarizer and our qualifier with this t. As a remark, I would like to mention that maybe if some of you remember the formulas for the true function, we have that for a summary like this of this short form, we will have the following definition of the true function, and for the form with one qualifier, we will have the following one. And this is these formulas are the special cases of our previous formula. Well, the first one, the number 5, as you can see, is a special case of this one, where we have we can suppose that our qualifier is a fsta which is always equal to 1. And having this, we will get number 5. Okay. So now I will go to actually the topic from the title of our presentation. So to consistency of the summary. So as you can see, we have two properties that a summary has to satisfy to be consistent. This is a non-contradiction and a double negation. So if we have such a short form of fuzzy summary, the contradictory form will be the following. So we have here a negation of our linguistic quantifier, or we have a negation of the summarizer. So a non-contradiction property will be satisfied if the true value of the true function for the first contradictory form will be the same as for the second one, and it will be 1 minus the value of the basic fuzzy summary value for this one. Of course, here, instead of having this formula, we can use any fuzzy negation, but in the beginning, we have just this classic negation. And a double negation, as you can see here, this is the formula. We have two negations, so we have a negation for linguistic quantifier and negation for summarizer. So as you probably expect, double negation is satisfied when the true function has the same value for these two summaries. So actually, as you can maybe notice here, we have a reference to the paper from 2016, which was actually a kind of inspiration for us, because there we found this part, and we asked ourselves, is this negation which is here, is it the only negation, the classic negation that can be used, and if we could use something else. So for this double negation, so for this form and the form of number 7, which is this contradictory form, usually there were used two operators, classical fuzzy negation, as I said, and an antonym, so this kind of operator. And it was proven that if we the double negation property will be satisfied if we take such negation operators. So here we'll have a classical, for the summarizer, we will have a classical negation, and for negation for linguistic quantifier, we will take we'll use the antonym form. And for the non-contradiction property, it will be this property will be satisfied if we take classical negation for the linguistic quantifier. So having this together, because we want our fuzzy summary to be consistent, the negation of the linguistic quantifier should satisfy this equation. We can call it the functional equation of this form. And if we take a classical negation as the negation of this Q, we'll have the following formula. So that's a kind of a nice and very, I would say, equation of the simple form. And first, for this classical negation, we have some basic facts. For example, that if Q is increasing, of course, we assume that it satisfies this equation. If it is increasing, then the border values should be 1 and 0. And in the case of decreasing, again, the border values for 0 is 1, for 1 is 0. And if we consider any unimodal linguistic quantifier, it turns out it has to be increasing, so it can decrease. And the maximum, actually, the supremum, so the value of such sets of where this quantifier has a value 1 can't be greater than 1/2. But as I said before, we were thinking if Q can be defined, a negation of Q, if it can be defined in a different way. So again, if we consider that Q is an increasing quantifier, then for the previous equation number 10, here, instead of this, we have, of course, that this is a classical negation, and if we say that the negation of Q is some other negation, we get the following functional equation. So the question is, what kind of fuzzy negation N2 will satisfy this equation? And this equation where these negations are, let's say, commutative. For this equation, we have the following fact, that if N1 is not necessarily the classical negation, but in the open interval 0, 1, the values also be in this open interval. And if we take N2, which is non-continuous, but it has in the middle of 0, 1, it has 1 value, then this value cannot be equal to 0 or 1, so it can be the drastic, the smallest negation, or just the greatest one. And also we need to have that N1 has to have a fixed point. So that's another thing. But again, we can take more general equations, so we can have actually even 3 different fuzzy negations, and we may ask what are the solutions for that. And of course, if we choose, for instance, strict fuzzy negations, that such triplet will satisfy this functional equation. So this is a kind of an easy fact. However, also, what we also was thinking about, it was that if we have the negation of summarizer and linguistic quantifier, we had that our quantifier was composed with the classical negation, which is strong. So our question was, can we take any strong fuzzy negation? And the answer is yes. If we define negation of linguistic quantifier in this way, and or for the summarizer in this way. And also our automorphism will satisfy this condition, that then we will have the property of double negation for the summary of this short form. And so, for instance, we can have such functions that can be our automorphism, is just a function that has an inflection point in one half. And again, for some extended, okay, for the file summary of this extended form, we have the qualifier R. We also have the following proposition that if we have a T norm T that satisfies this equation, then the double negation property is also satisfied. So concluding right now, let me ask what are the solutions of the treatments of the last functional equation for the T norm T? And is this only product T norm? It turns out it will be just a product T norm. Having this result, it's only just a product T norm. But what about general form of fuzzy summaries if we have more than one qualifiers and so on? So this is what we would like to work on. Also, to answer the questions, what if we have different negations of one quantifier and fuzzy, and the summarized. Okay, so that was all. Thank you very much for your attention.
Thank you very much for your talk. We are a little bit over time, so please, maybe we have time for a short question.
Very rich can be satisfying those which are invariant under by activity.
Okay, yes, I think you're right. Associated.
Okay, thank you very much once again. There are several offers. Okay, now we will continue with the next stall, which will be given by Lubomir Antony. And we have several offers with him: Petr Eliáš, Jan Guniš, Dominika Kotlárová, Stanislav Krajči, Ondrej Krydlo, and Lubomir Schneider. The title is Attribute Implications in Heterogeneous Formal Context. So please take the floor.
I and my colleagues from Pavlo Jozef Šafárik University in Košice in the east of Slovakia would like to present our recent results from our regular seminars on fuzzy logic and fuzzy sets in Košice, devoted to the heterogeneous attribute implications. And our team consists of my former supervisor, Stanislav Krajči, and Ondrej Krydlo, my colleague, who was also present here in person till Tuesday. And then we have the colleagues from the Department of the Didactics of the Computer Science, our PhD student Dominika, and Peter Eliáš is also from the Mathematical Institute of the Slovak Academy of Sciences. Our basic motivation came from the fact that other colleagues from the Department of Didactics of the Computer Science collected some solutions of the teachers and students regarding the educational and computational thinking game, which is called the Blackboard. This game is involved in the activities in the teacher preparation study programs at our university. It can be used also like some propedeutics for teaching, for learning programming. And this game has the following objective, that we need to construct the program or algorithm to control the movement of the robot in the environment, in order to light up all the blue boxes in this environment. This game has several levels, but our aim was to analyze the solutions only one specific level regarding the decomposition of the solution into the main method and two functions. So in order to construct the solution, we can use the commands like moving forward, turn left, turn right. Even some levels can use the jumping, but maybe the most important are also the commands of calling the function var or calling the function to. So if we look to these solutions, we prepared more than 60 solutions by students and the teachers who are qualifying for the teaching the computer science and mathematics. And two examples of quite opposite solutions are present in these figures. On the left, we can see quite linear solution in which the student used the sequence of steps, but he doesn't use the functions in the way to collect some repeating parts. Yes, of course, there are the functions calling here, but it is only because this environment has some limited space for commands. So it was not for some hierarchical decomposition, but only for some need to specify the solution. On the other hand, we have quite hierarchically decomposed solution in which the student specified some repeating parts of this solution. And this code is also the effective, and we will see later that it will consist some optimal solution. But first of all, we had the solutions in this graphical form. So we need to code this solution into the text strings, and this is our code. This is the word in which one letter corresponds to the one command. For example, F corresponds to the moving forward. This is lighting the bulb. This is calling the function one, and this pipe corresponds to splitting the program to these three parts. So after this pre-processing part, we also in GraphWiz generated the state diagram of these solutions because we needed to understand different strategies of the students. And we can see that someone started to move forward, but someone started maybe not naturally turn right and then go in this way. So they were different strategies how to move. And we can see that we have some not linearly ordered strategies. And it will be important also later in our theoretical results. Then at our seminar, we started brainstorming which attributes can be extracted from these solutions. There were several ideas, but finally, we summarized more than 20 attributes from these solutions. These attributes were numerical, but each of these attributes has some specific range of values. For example, we represented the number of the used commands, number of the executed commands, the used recursion or direct or indirect, if some solution went out from the environment and so on. And moreover, now it was the most interesting and most important part, how to explore dependencies between the solution of the students or dependencies between these attributes. And as we have already seen in the today's morning invited lecture of Stefania Boppa, very powerful method of data analysis and powerful method to explore the dependencies between the attributes is formal concept analysis based on the lattice theory. And our method was the following, that at the beginning we had some images, then we coded these images like some text, and from this text we generated the tables. And our aim was to explore these dependencies between the attributes. So this method is not new because we know that in literature we can find two ways. One way is of the attribute implication. The second way is the way of the association rules. They have many similarities, but many times they are investigated separately. And in this attribute implication, there are many interesting theoretical results, how to describe the minimal set of the implications. Giggs and Duquesne or Luxemburger studied also the partial attribute implications, and also attribute implication were included in the monograph of Ganter and Wille, the main book for formal concept analysis. On the other hand, in 1993, Agrawal and his colleagues started to analyze data from the supermarkets in the United States, and they analyzed the transactions in market baskets. We had some transaction of the customer, we have some items, and they specified some measures like the support, confidence, lead, and many others, and found the most known association rule in the world that if someone will buy the bread, then he will buy also the butter and milk and so on. But in 1999, the three different groups in the Germany, United States, and the France started to explore the connections between the formal concept analysis and association rules. And some methods from formal concept analysis and the construction of the concept lattice can help to reduce the number of association rules and can also generate effectively these association rules, not too so time consuming to generate all of them. So if we will look to the Gunter and Wheeler monograph, we will find the following definition of the classical attribute implication. So in this definition, there is no need to use the notion of implication because attribute implication between attributes in the set A is defined as a pair of crisp subsets. So this basic definition from this monograph is very simple. Only we have the pair of two subsets, and it is used to denote by this right arrow. First subset is called the antecedent, the second subset is called the conclusion or consequent. And in this book, there are also presented the results about some validity of this attribute implication in the formal context, also about some non-redundant set of the attribute implications. But for us, from the point of view of this whiteboard, it is very useful to find some implication in the form that if some student went out from the environment by the robot, then maybe the solution is not optimal, which can be represented by such object attribute table, in which we have the students and the attributes of their solutions. And we can specify some attribute implications which are valid in this table, but we have also some counter examples. In 2015, the group from the University of Malaga, Manuel Enciso, Manuel Ojeda, Ciego, Pablo Cordero, and Angel Mora and Carlos Rossi presented the paper in which they applied also simplification logic in connection with attribute implication, and they investigated the application of these attribute implication in the social networks. And they presented the formal context from the formal concept analysis point of view, in which we had the objects, the hashtags, and as the attribute, the mass media. And they found some interesting implication, like if we will find something in BBC News, then we will find it also in CNN and so on. On the other hand, again, the Stefania Boffa in the morning invited lecture presented some fuzzy extensions of formal concept analysis. And for these extensions, very important results are from the aggregation functions and results from Professor Messier, Kalina Hutnik, and so on, which are also incorporated in this fuzzy extension, in some fuzzy extensions. And each of these extensions of formal concept analysis has some advantages and can work with different types of data. And there are also some researchers here at the conference, for example, Josef Poč, Radomír Haláš, Manuel Ojeda, Ciego. And these approaches can help also to understand dependencies between the attributes. So in this way, maybe we can take the definition of Professor Bielovarek from 2006, in which the attribute implication were extended also in formal concept analysis from the fuzzy logic point of view. And the definition is the same, but now we will not take the pair of the crisp subsets, but pair of the fuzzy subsets, which can act, for example, on the residuated lattices, complete residuated lattices. From the computer science point of view, this structure can help to speed up the computings and also for implementations. And again, we can explore which of these implications are valid in the fuzzy formal context and which are not valid, for example, in degree 1. So the fuzzification can be applied not only to the degree of the attributes, but also to the degree of this attribute implication. For example, we can see that this object has value only 0.2, but we are expecting 0.3. So this is not valid in degree 1, but only in degree 0.9. And very important for our research was also the package FCAR, which was prepared by the group of the University of Malaga again. which is implemented in the programming language R and which allows to generate these fuzzy attribute implications. We can see also in the Fuzzy Cell Systems journal that nowadays, in January 2024, it was published a paper about attribute implications in multi-adjoint concept lattices with edges, which was also prepared by the group from the University of Cadiz. So our aim and our results can be divided into two parts. In the first part, we generate and interpreted the fuzzy attribute implications on these attributes from this whiteboard game. But then we realized that to analyze not linearly ordered strategies of the student, we should also extend these results for some heterogeneous extension. We will explain it. But first of all, we started to fuzzify the attributes. There are only two examples of count of executed commands. Minimum was 30, maximum was 70. After the fuzzification, this should be also the infimum and supremum. We had the values from the unit interval, and we found, for example, this attribute implication. If the solution is correct, and the count of executed commands is in degree 0.2, then this student was calling the function f1 in degree 0.5. Maybe the better interpretation will be in the original values, but our aim was also to include these attributes which are not numerical and which will provide some dependencies between the strategies. So we started to work on these definitions of so-called heterogeneous attribute implications, in which for each attribute, we can take different complete lattice. So one attribute can have complete lattice with 3 elements, another with some 5 elements. They can be different linear ordering or partial ordering and so on. Then we define the notion of so-called heterogeneous fuzzy subset, such that each attribute can have a different structure. And then also a heterogeneous attribute implication will be the pair of two heterogeneous fuzzy subsets. And then we also represented the condition when this attribute implication is fully satisfied in this heterogeneous formal context. This corresponds to the classical conjunction in this heterogeneous environment. And this index means that this conjunctor can be different for each object and also for each attribute. So again, we can have some different conjunctors on each pair of object and attribute. So if we look to our game, B can be the set of student solutions, A can be the set of all extracted attributes. Then we have the system of complete lattices, so we have some fuzzy relations. And then we export the question how to define the partial satisfiability of this attribute implication. So we use the known notion of degree of subsethood. Then we use the linguistic hedges and two special cases of globalization and identity. And the structure of our theoretical results can be divided into these two parts. So first, we studied the connections between the degree which attribute implication holds in the formal context, then degree to which attribute implication holds in intense, because we found that there are some connections. And there are also connections with the degree of the subsethood of consequent in the closure of antecedent. But Peter Wojtasz from the Charles University in Prague recommended us to look also for some connection with Luha association rules. This abbreviation means General Unary Hypothesis Automaton. It was presented for the first time with Professor Hayek, and they used, instead of checking on the satisfiability of the antecedent and consequent, also the contingency table, in which we can have 4 values. So we are checking the count of objects which satisfy the left and right side of attribute implication, but also bit negation. And therefore, we can change little bit quantifiers used in the attribute implications. And they presented, for example, instead of P implications, also so-called double P implication, P equivalence, average dependence, and some other measures. And these we are trying to incorporate also in formal concept analysis. But in conclusion, we would like to put emphasis that also attribute implications, but the concept lattices help us to discover some interesting cluster of the students. And at the beginning, I presented two quite opposite solutions, and we can see that this linear decomposition is here, and this best solution or optimal is also in the another cluster. So as the conclusion, we found that for the teacher, this visualization and attribute implication can help to recognize the heterogeneity in student solutions. It is recommended to use for the tasks which have multiple solutions. And we can also construct or to form some heterogeneous team of students based on their skills in some solving tasks and so on. And that concludes our presentation. Thank you for your attention.
Thank you. It was a very nice talk, very interesting. So are there any questions or comments? We are on time?
On time.
Yes, yes, yes. I know. Yes. I'm sorry because I'm not a very big expert in this area. I didn't prepare any question for you. I'm sorry for this. Okay. Okay. Thank you. Thank you so much once again. So we will continue with the third presentation. The title of this presentation is on the T powers of zero in the invariance property on fuzzy implication functions. We have several authors. The presenter is Rachel Fernandez Peralta, okay, and this joint work with Sebastian Massanet, Andrej Kazemanova, and Arnau Mir. Please take the floor.
And I want to say that this presentation is not the usual presentation I offer in conferences, because what I'm going to explain is a problem we found in the reviewing process of my PhD thesis. And this problem was found by Andrea Mesrada-Tumankova, so I want to thank her. Let me start by introducing the problem. The problem we studied was related to linguistic modifiers. Linguistic modifiers can be studied from the approximative aspect of language, and there are words that change the meaning of a sentence. For instance, here you have two easy examples. And linguistic modifiers in body logic, and also called body hedges, are functions that change the shape of the membership function. So they can be defined like this in a very general definition. And classical examples used by Frade in 1972 are the concentration or the dilation. But there are a lot of linguistic modifiers and different considerations. The ones that were considered by Frade were powering modifiers, defined as the powers of the membership function. Here you have a graphical example with a Gaussian membership function. Here you have the hedges, and here the corresponding membership function. But there are other linguistic modifiers, for instance, shifting modifiers. But in this presentation, I will focus in this type of linguistic modifiers. So the problem we studied was related to this paper of Mizumoto and Zimmerman, that in this paper, the authors studied this example applied to different inference methods. And particularly, they use linguistic modifiers, and these linguistic modifiers were the typical ones, which is the concentration and the dilation. And in 2017, Massanet, Recasens, and Torrens introduced a new property on fuzzy implication functions inspired by this example. In particularly, they introduced this property, which is called the invariance, that says that if in the previous example, the conditional is modeled through a fuzzy implication function, and the linguistic modifiers are powers of continuous tenors, then the truth value should remain invariant. Because if you see here, the same linguistic modifier is used in the antecedent and the consequent. So I said that these are considerations because not many people use fuzzy implication function there, or I couldn't find very much literature about using powers of continuous tenors as linguistic modifiers. I just recall here, if you don't know the definition of fast implication function, fast implication functions are binary functions that are decreasing with respect to the first variable, increasing with respect to the second variable, and they fulfill the boundary conditions in the definition of the classical operator. Like is typical in the study of fuzzy operators, this definition is very general, so there exist many families of fast implication functions fulfilling further additional conditions. On the other hand, powers of continuous tenors were deeply studied by Walker and Walker in 2002 and can be defined for any continuous tenor and any positive real number. But in this presentation, we will focus on the continuous Archimedean case, because in this case, we have an additive generator for the tenor and we have a nice expression for the powers. So if we consider now powering modifiers as powers of continuous tenors, we can obtain different families of linguistic modifiers. If we pick the product tenor, then we recall the powering modifiers used by Zare, but we can use other tenors. For instance, I select here one with a parameter, and we obtain different family of linguistic modifiers. And since here we have a parameter, we have flexibility in the selection of the linguistic modifiers. And this is the case for strict tenors. We can also consider nilpotent tenors, but since nilpotent tenors, they have a zero region, the linguistic modifiers we obtain are different than in the strict case. They have like more particular behavior. So the invariance property is a quite popular property in the field of fast implication functions. Here you have the original paper, and from this paper, several further studies arose. There are people that study power-based implications as a family that fulfill the property in many cases. Other people study related properties, for instance, considering the powers of Tekonon. This is a work from Michał Wasinski. And in my case, I study the characterization of the property. I study all binary operators that fulfill this property. And what I'm going to explain here, as I told you, is a problem we encountered studying this problem. The original paper is from 2017. The authors introduced the property, and then 2 years later, they found a mistake in their paper and they published a corrigendum. But then 3 years later, I found another mistake in this paper. In particular, I found a mistake in the characterization of all binary operators that are invariant with respect to nilpotent tenors. So I was happy because I corrected that result, but then in the reviewing process of my PhD thesis, we found another mistake. So this is what I'm going to explain today, okay? Particularly, this was the original result of the characterization of all operators that are invariant with respect to nilpotent tenors. So the operator should look something like this, and this was the region in which these conditions should be imposed. And I introduced this counterexample, and in fact, I proved that the expression should be the same, but the region should be the whole interior of the unit square. Okay, so I defined the family of fast implication functions which are invariant, and the structure was something like this. So what was the problem? The problem was that the original definition was this one, and the authors considered 0 and discard the powers that were different from 0. And in fact, I interpreted the property like the original authors, but in here there was a mistake. I also commit another mistake, which was to discard 0 here. And you will be wondering, is this an issue? Yes, it is, because in the strict case, the power is 1 if and only if x is equal to 1, and is 0 if and only if x is equal to 0. So in the strict case, the two definitions are equivalent, and my results were also valid. But in the nilpotent case, since the nilpotent tenors have another structure, here we have the power is equal to 1 if and only if x is equal to 1, but here 0 power to r may not be 0 for r less than 1. So it may happen this situation. And this situation affects the behavior of the operator when using the invariance property like this. So we for this presentation, corrected that result. And in the general case, when you study a binary operation, this is not much of an issue because I only had to include 0 here. But since we pick that result and then impose the properties in the definition of a path implication function, the behavior changes. Particularly if we consider the case without 0, we had this structure. This is what I did in my thesis. But if we consider the 0 and the nipotent case, then we had to impose this one region and also the pagination changes. So what we do is we redo all the results of the study of the additional properties apart from invariance. And then my idea of this presentation is at the end, decide which convention is better. So the new results are that we are going to study for this new definition the additional properties we already studied, but now with the considering the powers of 0. So the results will be presented in diagrams like this. In here, you will see the results without the power of 0, and here the results with power of 0, in which we have to impose this one region. So the first property I present is the identity principle and the ordering property. In this case, the solutions are the same, almost the same, because since essentially these properties are imposed in that one region, so there was no problem here. The only problem is that the Fuzzy negation, if we consider 0, depends on this free function, where here was arbitrary. In the left neutrality principle, also the solutions are very similar. The only, again, the Fuzzy negation now has to be 1. But for other properties, for instance, the neutrality principle with respect to E, we had this nice solution that depended on the additive generator. But now, if we consider the power of 0, we have no solutions. This is obvious because here we cannot impose this one region. And for instance, this solution was very interesting because it was related to other families and related to an open problem. So if we consider the 0, we have no solution. For the exchange principle, something similar happened. We had these solutions that depended on the additive generator, also that depended on an arbitrary function. We had very flexibility of choosing an operator fulfilling the exchange principle and invariant, but if we consider the power of 0, we only have a solution that is constant to 1. For the law of importation, there was no significant changes because the only solution we had were constant. But now, of course, this constant has to be 1. And to the final one was the T conditionality. And this one also, we maintain some of the solutions because the original solution was something like this, and we had some flexibility here. But if we consider the power of 0, the only thing we are losing is this zone that now has to be 1. So, to conclude, what have we done? We have adapted the definition of the invariance property, now including the powers of 0. We have redone all the study we had already done for the new definition, and we have shown that if we consider the power of 0, we somehow lose some of the interesting solutions we found by making a mistake. So, as future work, we, for instance, when we finished the original work, we wanted to consider the continuous non-Archimedean case, and also we want to consider the obtain operator in practical applications. But now we have the problem that what should we do? We should include the powers of 0 and assume that we are losing all that solutions. And the other option is we can maintain the definition was originally wrong, like another alternative definition. So that's all.
Thank you. Thank you so much for your talk. It's very nice to see that mistakes are normal. Okay, fine. So please, do you have any question or remarks? Maybe not. I'm sorry.
If someone has any suggestion, can tell me later.
Yes, yes, you are right. Okay, thank you so much. So now we will continue with the last talk. The last talk will be given by Michaela Brunetičová and Brunetičová. Bruteničová. Okay, I'm sorry, Bruteničová. This is joint work with Professor Janiš, and the title is Implicators on some finite lattices. So please take the floor.
I'm a PhD student from fsta, and I would like to present myself in study applications of NPLTC. Here is the definition of implication, which you could see. You could saw also in the previous presentation. Also, you could see the maximum implication, which is possible to construct on every lattice which you have, because this implication is defined for a bounded lattice, not only for interval 0, 1. There could exist also some incomparable elements. There are lots of classes of implications. There are lots of additional properties which we could assume. But we are inspired by the research about residual and SN implications on finite lattices. So imagine we have a lattice with, for example, the element. You could see a definition of residual implication, also of S implication, which is for the chains. So we could use maximum instead of supremum, and also we use the P norm instead of S conorm. And also we work only with a strong negation, and it is known that there is only one strong negation on chain. And here is a formula of that negation. We were inspired by this work, which is down on the slide. It is about these implications on finite chain, where all elements are comparable, as you can see. And here is a result which was inspiring for us. So we have some T norm, then it generates some residual implication as and S implication. It's clear that it depends on the T norm, but I didn't want to use more indices. I hope it's good. But you could imagine some T here and here. And if the T norm is smooth and Archimedean, then these implications are equivalent. And that T norm looks like this. Lots of indices. Okay. So what is smooth T norm on chain? Here you could see a definition and also lots of indices, but don't be stressed if it's not very difficult. You have a T norm for some pair of arguments. And also every element on in chain had two neighbors. If it is not 0 or 1, it has two neighbors. So we have this value for two arguments, and if we change one by his neighbor, then the T norm for this pair is same, or it is a neighbor of that original value or original arguments. So it is not very difficult. You only move for arguments and you look on the value if it is changing a lot or not. So also it is well known that if we have a chain with P elements, which are between 0 and 1, then there are two to P smooth T norms on that lattice. And also it is well known that there is only one Archimedean smooth T norm. It means that there are not idempotent element for this T norm instead of 0 and 1. So how that smooth T norms look like? In this work, which I was talking about, there is also some characterization of the T norms. It depends on the set of some specific elements, which are idempotent elements of the T norm. So you choose the set of elements, and you are able to create a T norm which is derived from this. Okay, also it is possible to characterize residual implications, which depends on that idempotent element, as you can see here. It depends on Tino because these idempotent elements are characterization for the Tino. Maybe you are waiting for characterization of S implications for blockchain, but I didn't use it for the presentation because now we are interested for residual implications and later for S implications. Okay, so half smoothness works on lattices. I chose definition because without indices. It is what I was talking about, but I defined some covering that alpha covers beta if it is a neighbor of beta, but there is a direction of covering. So x1 is covered by x2, x2 covers x1, and x2 is covered by x3 and x4. It is not complicated. You could imagine it on the picture. So we have smooth species and how these smooth looks on them. We could have different kinds of lattices. For example, if we have this group where there are some segments where are more than 2 elements, which are incompatible with some other one, then there is no smoothing norm here in this board one. But here, if we have only this segment, it's possible to construct smoothing norm. And we could use a smoothing norm on chain for construction of smoothing norm here. So if we assume this chain with xm and this chain with x comma m, the same smooth pinion for that, which is derived from some set of idempotent elements, and we connect it, we split it together, and we add these values, which are equal to this one. They are equal because that smooth pinion is the same for here and for here. Then we could have some smooth pinion on L. And also it's possible to get two smooth norms if there is some indices which are bigger than m, and the value is xm, then we could choose also these options. So there is some rule that then we could have one or two smooth norms. Unfortunately, I don't have this rule now, this open problem for next work because there are lots of indices, it's not nice work. But we were working with a simple class of lattices where it was possible to characterize in some way. So for example, here, we have a lattice with this element. That exists 15 smooth nodes. I have them on the paper. I checked it. We have some software and so on. It's associated with everything else. And there are also 4, and 4 of them are Archimedean. And they imply 13 residual implications by the rule which was on the. So we see that the number of smooth nodes is not the same as number of residual implications. Expectable. And there is some rule that for one for smooth nodes there is one R implication, and there is also some formula for it, but it is still in process. It will be derived in future. So we are working with this lattice with one element here, and then we choose order for this one. For example, this one. We added some incomparable elements here to that position. And we derived that there is this amount of smooth nodes. And this amount is Archimedean from them. You could see here. We have characterizations also for other one, but the important thing is that they imply n+3 residual implications. It's not so much if we compare it with this amount of smooth nodes. So have a short look at it. I don't want to torture you with it a lot, but I have also other characterizations in order. Every theorem is described here. And also I described the implications So here is one for this group, one for this group, for one genome, and implications here, and one implication here. Then we were working with this lattice. It was simpler. Then we have only two n genomes. One is Archimedean, and there are two cases about R implications. If n is equal to 2, therefore R implications. If it is more than 2, there is only one implication. Okay, then we edit elements only down, and there are more smooth genomes by one. And also it is different amount of R implications. In this case, you could see it here, some conjunctions. And then we edit element here. Well, and there is a difference. We have 2n Archimedean genomes, which would be interesting that it depends on them. So what do you think? If we have these residual implications, it's possible to construct some S implication, which is equal to some of them, but it depends on Archimedean genome and so on, and negation. Things no, it was expectable because if we have a lattice, it is not so nice as chain. Chain is better case, better for work. So the result is not so nice for lattices, but we have the characterizations and we could work more and find some other connections between them. So where are the differences? We have only one strong negation for lattice and only one smooth Archimedean genome for lattice. In these cases, where the lattice looks different, there are also different amount of smooth Archimedean genomes. You could saw it. And about negation, there is some rule. There is no strong negation, or there are two strong negations, and it depends on the position of incomparable elements. It needs to be symmetric. It needs to be in the middle, and the amount of elements is odd. So it is not nice for this kind of result, which was presented at the beginning. But maybe something different. So if it doesn't work, we need to work on something else and find some other result. So we could work with different lattices and so on. For example, we could change the definition of smoothness, and then we could use also previous lattices. This is for chains, so don't be confused if there is +1. It depends that it is a bigger element than X. And this is other formula for smoothness with using of distance and so on, but it is still the same idea. But the difference is here that if K is equal to 1, it's classical smoothness. But it could be also some other number, and we are interested in different distance between the original value and changed value. Also, so this is one way which we could try for next research. Or we could be interested in genomes in general, not only smooth genomes. For example, in this second work, we approximate some numbers of genomes on these lattices, also with some interesting properties there. So we could change genome, it could be genome in general, and we could choose this lattice. So here is some characterization of residual implication on this lattice. There are some specific values and constructions and so on. I am sure that you will be faster in creating it on paper than I created it in LaTeX. It was terrible. It's this picture here for a long time. Okay, so it is not so complicated, but there are some values which is not possible to determine in one way. There are more options, for example, here. It depends on genome. So the genome is really important. But we could create some approximation of some estimation of that amount of implications. And the good news is probably that it couldn't be more than this value. So this is an upper bound for the number of residual implications on this lattice. You could see that if we change one argument, the values are changing them a lot, so it's not smooth or fast smooth or nothing. I think not so nice, but the good news is that it's not more than this amount of residual implications. Okay, so I wanted to talk also about these options which about which we were thinking about. But I think I don't know anything new, and thank you for your attention.
Thank you very much. We are in time. It's very good. Thank you for your very nice talk, because for me it was interesting that you prepared several examples and it was very nice, I think, for understanding. So are there any questions or comments? Yes, you can.
Want to be sure that on the second slide you showed some example of the in-phase implication, and you told maybe that this is the maximum one on the lattice. You told that this is maximum one on the lattice or not, or but this is the maximum one or not, because in my opinion this is not the upper bound in my opinion, because you can have the one the zero when x is equal 1 and y is equal 0, and on other points you can have just 1. So you don't need to have the strong negation here when x is equal 1. So you can have only the values 1 and 0, and then you have also the implication, because from the boundary conditions you have only assumptions about the 1 and 0. Yes, so you can put that only in one point is 0, and in all other points maybe this is maybe for the residual one, or it's maybe yeah, but not for the all the implications. Yes, and at the end you have this upper bound, but this is you told about the upper bound, but this is the, how to say, it is approximation, or this is this upper bound, only upper bound. Yes. Okay, so first it can happen that the real number is smaller, but yeah, okay, thank you very much.
Okay, thank you for your answer. So thank you once again for your talk. So let me close this session. Enjoy football match, enjoy gala dinner, and for cheerleaders we have meeting point at 4. See you. Bye.